Welcome everyone to one of the final tracks of reInvent. I hope you've all had a great time and thank you for coming to this session. So my name's Ryan and I'm your host today and we're going to be talking about integrating on-premise resources. So the assets that you have in your environment and how you can leverage the cloud in combination with those, some of the technologies in play. And listen to some customer stories about how people have done that and what they do in real life about how you can sweat assets that you have, how you can make judgment calls about what should live in your existing data centers and what should live in the cloud. So with that agenda, we're going to talk about some of the sort of three fundamental constraints of traditional data centers and introduce the idea of the elastic data center in the Amazon Web Services cloud. Look at some fundamental services that are involved in building up that elastic capability around the data center and how you can integrate those on-premise resources into that. Some examples and patterns at play. And then we're going to have Paul from Apollo Group, a principal architect, who's going to come up and he's going to talk around what they've done, how they've made the choices that they've made, the decisioning they've gone through to determine what should live in the cloud, what should not, and how they've bridged between those assets on their traditional facilities into the cloud. So traditional constraints, okay? 3 traditional constraints to take away, and hopefully these will resonate with you at some point. So first is the capacity, right? So in your traditional facility, you have a fixed amount of resources, okay? And getting new resources and doing new projects means that you need to add more things, whether they be physical servers, whether they be requisitioning and provisioning VMs in a virtualized world. At some point, you hit the edges, and you can't do anything else, okay? So traditional facilities, capacity is a premium resource, right? So at some point, you outgrow the size of the facility you have. You don't have enough racks, you don't have enough power, you don't have enough cooling. So being able to move outside of that and get some resources real fast is where the elastic data center comes in. So capacity is constrained and is a premium resource. Second thing is agility. So traditional facilities, to get something done, you're going to have to quite often raise a list of requirements. You might need to provision servers. You need to think about load balancers. Think about firewall changes that you might need to make to get something to happen. Think about storages and database and file systems that you might need to enact some sort of project. So you kind of give those things to your team to go do, and it takes some time, right? So you have to raise tickets. You've got to get approvals. You go through a process. And sometimes the resources that we want to build out, we want really quick. You know, Friday afternoon, we want to try something out. We want to run a project for a week, a fast dev project, but it can often take 2 to 3 weeks maybe to go through a process of requisition and resources. So being able to have resources on tap that you can pull in quickly is a great idea, and it's something that we'll talk about how you get out of AWS in a moment. So requirements can take a long time to fulfill in a traditional facility. Third constraint is cost, right? Things cost money, okay? And quite often, we have projects that we want to deliver, and we make some sort of evaluation about whether they're going to be approved based upon maybe the impact, some sort of scorecard process we might go through, impact and cost to determine whether they actually are going to happen or not, because of constrained resources, because resources are at a premium, and we make those decisions. So project X here, we're going to deny. We might, and then maybe some of you have had this process happen, or you're part of the decisioning process in your internal environments now, which decide what project should happen or not. Okay? And project X, project Y, project Z, one of those will go through, and they may not be the best projects to do, but because of cost, because of constraints, they're the ones that will fit in the slots that you have available in a facility. So cost, agility, and capacity constraints are really 3 reasons why going into AWS and hooking AWS back into that facility creates an elastic edge to your data center. So how do you achieve that? Well, the elastic data center is all about flexible on-demand facilities, but facilities that are integrated in such a way that they look and feel like your on-premise resources, okay, so that you can run internal applications that maybe have no internet-facing elements at all and leverage those back into data systems that you have running internally. Okay, so the elastic data center is not just about being able to approve projects and spin up resources as you need to and throwing them away as you need to and when things are complete. Being able to bring very large compute instances on demand to support a project and then throwing them all away when you're done, that's, of course, general benefits of cloud computing in AWS. But the elastic data center is about wrapping all of that resource in some of the traditional security constraints and controls, the policies and procedures that you have that govern your internal processes and your internal facilities. So it's about creating extensions to your data center with classic EC2 resources, with middleware such as SQS, data pipeline that you heard about today, but hooking those back and integrating them with on-premise applications and resources. Maybe running databases in your internal data center and web-facing systems and applications that talk to those databases out in the Elastic Cloud. So what we're going to talk about is some practicalities about how you achieve that in this session. So practicalities. Number one is network. Okay? So if you want to extend your existing data center into the cloud, the first thing you're going to want to do is extend address spaces into the cloud to make it look and feel like it's your network. And the controlling part of that is the VPC. So a VPC separates customers. So in the traditional EC2 world, everyone's in a shared address space. So customer A, B, and C, you're all going to get IP addresses or public addresses from a common pool. Okay? And you're mingling with other customers at a network level. So asserting some control is via VPC. You can, in effect, raise yourself out from the general mass of network traffic and assert your own address spaces, such as here, I've got a 10.0.0.5. I might have another subnet there, 10.0.1. Okay? Asserting control and getting logical separation at a network level and defining what those address spaces are so that they can look and feel like extensions of your data center and your existing network. So a VPC essentially allows you to create private subnets, user-definable address spaces. You can define the address space that you're using. You can define up to 20 subnets as a soft limit, and you can expand that out. So you might think about putting private resources that you want to control in a private subnet and control at a network level the security of what can access them. You can tie these subnets back to your existing facilities via a virtual private gateway, and we'll look at some of the technologies at play there in a second. So we might have hardware-terminated VPN, for example, that you can string from your existing facility. You can put things in a public subnet, and you can control the access to those resources from that via an internet gateway, all within your control within the VPC. So you can route things out to the public internet, and you can publish those things for access from the internet. And of course, you can control the networking between private and public subnets. Okay? So a VPC allows you to assert that control, which is different from EC2. And this is a fundamental part, really, for enterprises extending their existing data centers, their existing network ranges into the cloud. And there's a few patterns you can achieve with VPC. You might just want to assert some level of network separation and have publicly facing internet systems, in which case you might create a public subnet and expose it to the internet via a gateway. On the flip side, you might have an internal-only facing system. You might want to spin up a SharePoint service, for example, in AWS. And you can do that, and you can assert just a private subnet, by default, no access from those systems to the web, and then string those back with a VPN into your facilities. Okay? So your users would have to come in via your own existing corporate network, maybe, authenticate against the VPN, and up into the cloud, into a little bubble where you're running private-facing systems. You can, of course, assert control, such as a web app with a private and a public subnet and a NAT in between. You might have data tier and a private subnet, and you might have your web servers and a public subnet. And there's the pattern that I showed you at the start, where you can put that hardware VPN endpoint into your private subnet and give yourself administrative access to those back-end servers. Okay. So security groups in VPC look and feel a bit different from EC2. So you get the idea that you can assert a level of control that you can't in public EC2. And security groups, the firewalling element, are expanded when you're in a VPC. They support inbound and outbound rules. Okay, they have support any internet protocol. And I think one of the fundamental things that makes them different is that you can move security groups and instances in and out of security groups. In EC2, when you launch an instance, you assign its security group and it's fixed. You can only then update that security group. You can't change that instance into a new security group. Within VPC, you can move things around. So it gives you a degree of control which is quite powerful. Right? So even just for general work, you may consider using a VPC to give you this level of control. Another thing that's different in VPC is instance addressing. So I mentioned that sort of public address space that you get. In public EC2, everything gets dynamic private IP and a dynamic public IP. You can, of course, stick elastic IPs on instances if you want to. But we provide you with DNS names and entries for those instances. So when you start an instance in EC2, you know that public DNS that you can use to access it and SSH onto it. In VPC, it's got a finer level of control. So we get a dynamic or a static IP address assigned. You can choose what you want assigned to that instance. You can control the DNS service that's running inside the VPC. You could even provide your own DNS server that you're running inside that VPC. And there's no public IP address by default. So instances in a VPC start, and they're private. There's no internet-facing access to those systems by default. Okay, so security by default. So you've created a secure network structure, and your network engineers will love the control that they can assert on a VPC. It's all familiar territory, it's all routing tables and so on. But once you've created that, you want to connect to that VPC in some way. So how do people do that? Well, there's, of course, public internet, right? So you can get to these instances over the internet just as you can in public EC2. But going a step further, you want to control access over a VPN. So we provide a hardware endpoint within AWS, and then when you start a VPN inside a VPC, you can download a profile for your endpoint, your router, and if you support BGP, it will negotiate the routes up into the VPC, or you can statically define those routes as well if you don't have one of those pieces of kit. Okay, so you might have a Cisco router in your office, and then we provide, on an hourly basis, the rental of the hardware endpoint within the VPC so you can create the IPsec tunnel. So IPsec tunnel, negotiated routes over BGP, and you're up and running, and we know how to find resources in AWS when you address them internally over IPsec. But there's another way you can get connected. If you're not comfortable with public internet, you might have very large bandwidth requirements that you really want to push up very large data sets into servers running in your VPC, or you might have latency requirements where you want consistency. You want to know what the latency is to your resources in EC2. And you can do that over something called Direct Connect. And Direct Connect is essentially a dedicated connection that operates between a Direct Connect location, and the location is shown there, and then the last mile, if you like, can be supplied by probably one of many network providers you probably already use in your environments already. Okay? So they can hook you up, cross-connect you in a Direct Connect location. So looking at it logically, what we have is is a dedicated connection over an Ethernet transport, okay, to a location. And you can choose a port of 1 gigabit or 10 gigabits per second, and you can have as many of those ports as you like. Okay? So you can multiplex this connection and get very large bandwidth, dedicated pipes, if you like, into the AWS cloud. And you can spin up more than one of these to diverse hardware endpoints within the VPC also. So for fault tolerance, you can end up on 2 different hardware termination points within AWS, and they'll have automated failover between those links. Okay? So you can create a highly available, dedicated connection, right? Looking and feeling like a traditional connection maybe between your primary and secondary data centers that exist today. But of course, you can put these things together. So you're not just using Direct Connect or public internet. You would typically use these things in tandem. Because what you want to be able to do is to have a fault-tolerant primary dedicated link, but if those links go down for whatever reason, you want to be able to flip back to an internet-carried VPN tunnel. Okay? And all this failover can happen as a little sequence that you can define if you're a Direct Connect customer. And you can simply go into the console and order one of those Direct Connect links. And many partners in the partner network will also sell you a slice. If you don't want 1 gigabit, you maybe want 100 megabits. Many of these partners will sell you a slice, a prorated slice of the last mile link as well. So great for maybe edge locations, branch offices, or putting big trunks into your primary data centers. So you can connect to the VPC, and you can assert control via a VPC. So now you're connected, what would you do? You would use the Elastic Data Center. So let's look at some of the use cases that customers are performing over these connections and using VPC. Firstly, is a very common use case is the management of data. So we all know that S3 is a fantastic place for storing data, that Glacier is a great place for doing long-term archive of maybe backups of databases or data that you might only have 1 copy of and want to keep for a long time. And Storage Gateway is a great entry point. That once you have that nice connection into AWS and you've got your secure area, that you can use the Storage Gateway to initiate some local volumes managed by the Storage Gateway. Okay, so you download a VM image, which is called the AWS Storage Gateway, install it on your local servers, and then start creating volumes on your disk arrays that you have internally. And then you can, of course, address those using iSCSI from servers running in your traditional facility. But what's happening is that the storage gateway is taking snapshots of those volumes and pushing them in a compressed form into S3. Okay? And then you can reconstitute those. So if you have a problem with one of those local volumes, you can pull back the backup file down via the storage gateway and restore, from a point in time, that volume. But not only that, these backups are essentially EBS snapshots. So you can also reconstitute those volumes in EC2 inside your VPC and recreate a server based upon that disk snapshot and attach maybe an AMI for a Windows server or a Linux server. Okay, so you have a choice of where you restore to. And that's called gateway stored volumes. But the storage gateway will also allow you, where you might have constrained resources in your traditional data center, you might not want to expand your disk arrays. You can use what were called cached volumes. So it works in a similar way, except what the storage gateway would do on your local drives is just do recently accessed data or frequently accessed data, and the rest is held in S3. And those older data want to be addressed. A bulb's gone, it looks like, so apologies. You see that one? It's the last one of the day. Come on, it's just the luck. Right. So, but what you can do is you can then address those again as iSCSI interfaces. You can have up to 32 terabytes of cache volumes, and you can sort of maintain a fixed footprint of disk size then. You don't have to keep expanding your physical arrays, and then you can get a relatively low latency link back to pull that data from S3 as you require it and as it's accessed. So a great way to expand into the cloud without having to add more physical kit into your facilities. Another use case that's really common once you've got that little private elastic part of the data center is dev test. So environments that you want to spin up fast, you might have many of them at different stages of an application, and that you want to throw away. So very disposable environments in a dev test environment, very fast moving. So you can spin them up and you can throw them off. And for the gamers in the room or those with children, you might know Little Big Planet 2. So Media Molecule and Sony Computer Entertainment. One of the big benefits they see in how they use and integrate to their existing assets is the ability to spin up those environments, to spin up QA environments, to spin up beta environments, and then throw them away again. But keep those things private, because these are things that, that pre-release of a game, they're not wanting people to find the public. So they're using VPC to expand these things and contract them, and then govern the access to those resources in the VPC. Some other use cases, and I'm sort of focusing really on a couple at the bottom there, that are common problems when you're dealing with sort of large-scale development and test environments, are workstations. So being able to have a bank of workstations that your developers can spin up and access that you don't have to worry about, maybe resource dependencies and conflicts that you might have that are commonly layered on top of each other for a physical workstation. You can have those all ironed out and have AMIs in the cloud that you can spin up to just do a particular type of development task and then throw them away. And build servers, because you've got elastic capacity, you can spin up loads of build servers, crunch through compilation of code, and expand back down. Again, stuff that can pull maybe source code from existing servers in your on-premise environment to do that job. Testing, similar sort of aspect, really. Where you've got constraints in a physical environment, being able to create a whole new copy maybe of a live system, maybe hundreds of servers, in AWS, do A/B testing, where you don't have that traditional capacity available in a physical facility, or doing load and performance testing. So we saw today in one of the keynotes, we saw an army of servers being spun up to load some of those sample applications. Again, all through this method, you can have access to the resources that you might not be able to get access to in your physical facility. I mean, you can do things like security as well, creating sandboxes for aggressive security testing. You can get really, create copies of your live environment and allow people to really try to pull it apart so you can be sure that your environment is going to stand up to public scrutiny. Things that you couldn't really do, you could normally have 50% extra capacity in your physical facility to create a whole new copy of live. And you can do that, and you can do it securely via the VPC. But it's not just about the latest, greatest internet applications. So many people are running things like SAP or Oracle apps, and testing things on those makes a lot of resources are required to install and create a version of SAP, from databases servers, the app servers that are running it. Being able to spin those up in AWS, because AWS is certified to run them from SAP Business Suite, SAP HANA 1, the in-memory database, or the branch office all-in-one SAP business solution. You can spin these up in AWS, and you can get these from the marketplace and one-click deploy them. And there are CloudFormation templates. And you can create a whole environment that you can then go and do your testing of your modifications or your workflows and your business processes and be secure in that they're working, and then throw those environments away when you're done. Another common use case is disaster recovery. Okay, so the basic sort of premise here is that to do 100% sort of guaranteed disaster recovery, you need two sites that are doing the same stuff. And all the stuff that goes on in your primary site, you're going to need to do in a secondary site. And you're going to want to be testing that and make sure that's live. So from routers, firewalls, the networking, licensing the applications that are running in those environments, the configuration of storage, servers, OSs, and so on. Okay, you need to dupe up what you have in your primary site. And you fail over into that environment, and then you recover from it when you're ready. Now, the basic premise here with AWS is that you can do disaster recovery in a secondary site with simply snapshot storage. You know, at the very basic level, you can create environments in AWS from stored snapshots. Okay, so you can reduce the secondary site costs. So how does that work? A common pattern is to use something called a pilot-like pattern. Okay, so where we keep alive a core data set and synchronize that into the cloud. And then you build the resources in that cloud data center and to keep them in a stopped state. So you're not paying for them. You're only paying for the storage of the volumes that would back them on EBS. And when you're ready, or when some sort of event dictates, or that you want to test your DR, you simply spin that stuff up and match capacity. You put a desired capacity on an auto-scaling group and go from 0 to 20, let's say, and build up the service in that environment. So it looks a bit like this. So we take a core data set, maybe a database might be your key element to support your disaster recovery, and you're constantly syncing that into the cloud. And we have stocked resources surrounding it, and when something happens, or you dictate that you're going to test this DR plan, you can simply spin up the resources, promote them to live instances, flip things like DNS, open up the VPN tunnels for your branch offices, and then you can be using that secondary virtual data center. Another common use case is big data. Okay? So if you want to do really big analysis and you want to have hundreds of servers maybe in a Hadoop cluster, these are things that you've either got to go out and buy brand new big arrays to install in your physical facilities, or you don't do it at all. Right? So another common use case is the ability to use Elastic MapReduce, because you can leverage that huge elasticity. So typically customers are pushing data on a schedule, and this is where some of the data pipeline comes in now, to enable you to take logs and so on from servers in traditional facility, as well as your cloud servers, and push them into a common bucket in S3. You then spin up an Elastic MapReduce job, which is controlled by a name node. That'll spin up the resources required to do a particular task. So you might go and get spot resources off the spot market to create the instances to do the Hadoop job. And you can obviously go really big on that, hundreds or thousands of servers, and when you're done, Elastic MapReduce turns off those resources. Okay, and then you can pull the results of the analysis out of S3 back into your local servers, maybe into your data warehousing or your analytics tools that are installed in your physical facilities. So you get the idea that there's many different use cases, but they're all fundamentally predicated on you being able to create a private slice of the cloud and being able to connect into that reliably, so you can treat AWS as if it's just an expandable part of your data centers. Now, before I get on to inviting Paul up, I wanted to talk you through a customer story from my home turf in the UK for a utility company called Haven Power, so providing gas and electricity. And they've used this DR use case as their sort of fundamental leap into the cloud to learn about a whole bunch of different aspects of dealing with cloud resources. They've got a full secondary facility running in AWS, all running in a VPC. They're running Oracle and SQL Server databases. They've got Active Directory and Windows file share, so a classic sort of environment. And it looks a bit like this. So they have direct connect and internet connection failover. So they've used that connection pattern into the VPC, into that virtual data center. They're synchronizing, there's dual root connectivity there. They're synchronizing Active Directory. So it's real-time replicating Active Directory. And this is one of their pilot lights that were always on. They're also using a pattern called Bastion hosts. So they've got hosts that are running in a subnet which are stopped. And when a ticket is raised to do some sort of remedial work in those resources, that ticket will start those instances and allow administrators to log on to that host. And from there, the VPC networking is saying that what resources they can and can't access within the environment. so a controlled, auditable logging point for admin access. Their second pilot light is their databases around their back office systems for doing things like billing of customers and metering. So they're running an Active Directory hot, and they're running databases hot. And all the other resources, like application images, all the different servers that they need to do are in a stop state. They're file servers. They've got desktop environments as well. So running Windows Server environments that their users can log into to use all their internal applications in the event of a disaster recovery situation, remote desktoping in. And all backed by durable storage and backups of things like their RDS databases running Oracle and Microsoft SQL Server. So you can see here how they've treated AWS in a very similar way as they treat their physical resources, but they've been able to create an entire secondary disaster recovery site without the cost of investing in a secondary facility. Okay? And when they're not testing or using that DR site, all they're paying for is the fundamental pilot lights to keep this thing alive. Okay? So that's some of the technology at play within extending your data center.